Hello everyone, welcome back. Wait a minute, this isn't your PowerPoint. That's right. This is not a PowerPoint. This is our class website. Now the reason I'm bringing this up is because I want to show you how to find the tables they're going to be using in a ton of problems. Now, because I'm going through this in a PowerPoint, I'm not going to be pulling up the tables every single time. That would just take too much time. But I'm going to show you the basic method to do so. So first off, you go to Connect website, or you can go to your physical textbook. It'll still work the same. Mine is just nice because I can just jump right to the table I want. You click the link for your textbook, and then if you go to this drop-down box right here, it'll bring you up the table of contents. You're going to scroll down all the way until you find your appendices. Now, if you're in English units, go to Appendix 2. SI units, go to Appendix 1. Now, when you get there, for most of the problems we're going to care about, we're going to be looking at a few different tables. So I'm going to go ahead and give myself the ability to write on the screen here. So web capture full page. There we go. So the ones you're going to be seeing the most are one, these three right here. Am I drawing? Yes, I am. These three right here, as well as these three right here. You also occasionally go to the ideal gas properties of air or nitrogen or other things later on. Those happen too. But these two are the biggest that you're going to see the most, especially as we go through the vapor cycles, the next chapter. Okay, now when I get there, what am I going to see? Well, we're going to go, first I'll show off the saturated water table, and then I'll do the ideal gas properties of air table. We'll do two of them. Yes, I'm okay with getting rid of that. There we go. So I'm going to go to saturated water temperature table. Boop. Now, when I go to the saturated water temperature table, what I'm going to see is, first off, it's giving me data as a function of temperature. Let me see, can I pull it up, the ability to highlight? Let's see. Don't often do this, so there I can. Nice, okay. I can highlight. That's not going to work as well. I'm just going to go ahead and capture the page. There we go. Okay, so it gives it to me as a function of temperature. You see that right here. So I have it at 0.01, 5, 10, 15, 20, all the way down the line. The second column is my saturation pressure. When I am a mixture, a saturated mixture of water, liquid water and vapor water, then so long as my temperature is constant, this will be the pressure I have. So when I'm going from being, here's our little diagram, remember this guy? When I'm going from being perfectly liquid all the way to being perfectly vapor, my temperature will be constant at that, and my pressure will be constant at the saturation pressure. If my pressure is greater, that means I'm now over here. I'm in a superheated vapor. If my pressure is lower, that means I'm a compressed liquid. So all those are possibilities here. And same with temperature if I was doing that. Then you're going to have your specific volumes, your internal energy, your enthalpies, and then going down the line, your entropies. Now, why do we need this table? Why do we have to come and look at this table? Well, the reason we have to come and look at this table is because I'm not always going to get data that perfectly falls on the lines here. I might find that they want to know what happens at 47.5. Okay? And oh, dang it, I don't have 47.5. Now, here's one little trick though to make sure that you're not wasting your time. 47.5 does not show up on this table, and it likely doesn't show up on the pressure table too. But before you go doing a whole bunch of interpolation, check your pressure table too, because you'll get different temperature options there. So I've got 5, 10, 15, 20 here. I want to get out of this and go to the pressure table now and see what it looks like, which I'm just going to scroll down to get to because it's right next. Here we go. What you'll see is I still have a range of temperatures here, but they're different ones. And a lot of times, one or the other of these tables will have the information you need. Okay. But you're not always going to get lucky there. Sometimes it's going to be right in between. And when that happens, it sucks. You got to deal with it. So let's figure out how we deal with it. Now, by now, I expect that you know how to interpolate. But in case you don't, this is for you. So let's say I wanted to figure out what happens at 162.5, right there. What happens when my pressure is that value? And we'll pick not specific volume. We'll do internal energy right here, okay? So I want to figure out what UF would be for my value of this pressure. I need it. Why do I need it? I don't know. I just need it for some strange reason. And so I have to calculate it. Or let's be a little more realistic here. Usually it would be more like UFG. So I'll do that one instead. Well, my pen has malfunctioned. There we go. Really slow on the uptake today. There we go. I got it back. Okay, so let's get UFG. Always fun when things mess up. Okay, how are we going to do that? Well, the way we're going to do it is by interpolation. That means I need to make a sandwich here. So I have a pressure above, I have a pressure below. That's sandwiching in my temperature. I'm sandwiching in my value for the pressure. I have a internal energy of vaporization above, I have internal energy of vaporization below. I got both of those. I got a sandwich there. And so what we're going to do is we're going to make an assumption. We're going to say, okay, if I have my internal energy, it might go something like this. What I'm assuming is I want to find this value in between. I'm going to say, well, this right here, that is a straight line. Is it correct? Technically, no, but it's close enough and these steps are small enough that we're probably okay. Now, if we want to make super accurate, I could fit 10 points and really get a good function for it. But why go to the trouble? And oh my goodness, that would take a long time. Unless I was using some sort of program to do it. Okay, now I've got those values, I need to write down what I call the low and the high value. The low value, I usually base it on pressure or temperature because it's a little bit more straightforward there. It's going to be these two right here. So P low is going to be equal to 150. P high is equal to 175. Okay, I have those. Higher pressure, high. Now here's where it gets wonky. If you look at the internal energy that goes with the low side is actually higher than internal energy that goes with the high side. You cannot flip those. If you call it P low and this is the low row, you have to keep on going all the way across and use that. So U low, I'm just going to write it down here, U low is going to be equal to 2052.3 and U high, beautiful handwriting I know, is 2037.7. Okay, now that I've had that, it's time to write out my interpolation equation. This is the same regardless, and it's not too bad. So what I'm going to do is I'm going to say U is equal to U low. So I'm saying that this is equal to my lower value, and I'm going to add something to that. What am I adding to it? Well, I'm going to add to that. First off, I have to give myself a way to know where I am. So that's going to be P minus P low. And I'm going to multiply that. Doing good? I'm actually doing good. U high minus U low, definitely running out of room here, over P high minus P low. And just to make sure that's completely clear, I'm writing this again here. That's U high minus U low over P high minus P low. Okay, so what is this? Well, it's honestly your y equals mx plus b equation. This right here is a slope. That is m. This guy right here is telling us how far along that line we are. That's more or less x. And this guy right here is what we're acting as our y-intercept to be. So that's all you're doing there. If you multiply this out, it will work every single time. Just remember, high minus low every single time. And it will always, always work, okay? It will always, always work. And I'll be writing this several more times in my PowerPoints, so you'll see it again. So don't worry about that too much. Okay, so we've seen how we interpolate. We see how we would get the values from the tables. With that, I'm going to head back here now. I'm going to show you one more table that will probably be helpful for you. And to do that, I'm going to have to completely, let's see, I'm going to switch to Appendix 2. Why Appendix 2? Because then I don't have to worry about sliding. The book is weird online, and that it won't jump if you're in the same appendix. I'm going to go to the ideal gas properties of air this time. Table A17E. E for English. So this one's very, very similar. One thing you'll notice here is you'll see S plus. Now, I don't like S plus, okay? I don't like S plus. It's a newer term that they've come up with for the newest version of the textbook, and I detest it with a passion. As such, we will still be using relative pressure and relative volume, the PR and VR, when we solve most equations, and I'll be showing you tables that are from the 9th edition of this textbook, which still have those, as they got rid of them and replaced it with what I find to be a very confusing term, S plus instead. So just know that for the future. Okay, that's it for this time. Thank you all so much for listening. Sorry for the technical difficulty in the middle, and I'll see you all next time. Bye-bye.